In the boardroom, the pressure to adopt blockchain is relentless. It's pitched as an essential upgrade to signal you are ready for the future. But strip away the marketing, and blockchain is simply a highly specialized, inherently inefficient database. It was designed to solve one specific engineering problem, allowing entities who do not trust each other to agree on a shared record of truth. This comparison table maps the exact technical trade-off. A traditional centralized system, like Visa's payment network, can process over 50,000 transactions per second. A permissionless blockchain, like Bitcoin, handles about 7. You are actively trading raw speed and structural simplicity for decentralized consensus. If your system already relies on a trusted central authority, bolting on a blockchain adds massive computational overhead. Latency spikes, throughput collapses, and your engineering costs multiply. Using a decentralized ledger to solve a problem that a standard database already handles is a massive misallocation of capital and processing power. To cut through the noise, researchers at ETH Zurich developed a peer-reviewed methodology to determine if an application actually requires this technology. Their framework functions as a strict logic tree. It ignores industry hype and relies entirely on technical constraints to prove exactly which database architecture a project needs. The entire matrix hinges on a single question: who controls the state of the system, and do the participants trust them? The choice between a centralized server and a blockchain is an objective mathematical outcome of your system's trust requirements. The flowchart starts with 2 baseline filters. Does your system need to store data, and are there multiple independent writers? If you only have one writer or don't store state, the path ends immediately. A centralized database is the most efficient choice. Yet, companies routinely try to force physical supply chain management and IoT tracking onto distributed ledgers. The vulnerability here is the physical-digital interface. An immutable digital ledger guarantees that data hasn't been altered after it was entered. But if a careless warehouse worker logs a counterfeit shipment into the system, the blockchain faithfully records that lie forever. Because you inherently have to trust the human or the sensor at the point of physical entry, you already have a functional, trusted third party in the loop. Paying the immense computational tax of distributed consensus is useless if the system remains vulnerable to human error at the loading dock. Contrast that with international finance. Banks constantly transfer massive amounts of capital across borders, acting as independent writers who need to interact, but who lack absolute trust in one another. To settle a cross-border payment today, banks rely on a web of centralized third-party correspondent accounts. This legacy routing adds significant friction, delays, and counterparty risk to every transaction. Let's map this on the flowchart. We have multiple writers who do not fully trust each other, but because they operate in a highly regulated environment, all participants are strictly known and verified. This leads directly to the permissioned blockchain architecture. In this model, a central authority, like a central bank, can act as a certificate authority, granting access to a restricted network. The consortium gains a shared, trustless ledger to settle payments directly, bypassing intermediate clearinghouses. The operational trade-off is that read and write access is strictly walled off from the public. It is a pragmatic compromise. Regulated corporate consortiums get the efficiency of shared infrastructure while retaining absolute control over privacy and membership. There is one final scenario: a system where the writers are mutually distrusting and their identities are completely unknown to each other. The Decentralized Autonomous Organization, or DAO, operates exactly this way. It functions through a set of smart contracts, pooling funds from anonymous investors who vote on resource allocation without any central management. Following the logic tree, when all writers are unknown and trust is non-existent, the only viable architecture is a permissionless blockchain. To maintain complete censorship resistance and allow anyone to publicly verify the state of the system, every node must process every transaction. This structural redundancy forces network throughput to drop to the absolute minimum. There is also a severe tension between transparency and privacy here. Because the ledger is completely open, concealing sensitive financial data requires computationally heavy cryptographic workarounds. If your application demands a truly permissionless network, your business model must survive high transaction costs, public data exposure, and extremely low processing speeds. We distill these constraints into an operational map, plotting trustless decentralization against speed. For enterprise leaders relying on trusted intermediaries, the centralized database sits top left: maximum speed, zero decentralization. For system architects building B2B consortiums among known but distrusting partners, the permissioned blockchain occupies the exact center. It sacrifices some performance to secure a shared private ledger. And for founders building fully autonomous, censorship-resistant networks, the permissionless blockchain sits in the bottom right, securing absolute decentralization at the total expense of speed. Elite engineering is not about adopting the most heavily marketed technology. It is about understanding the exact nature of your trust problem and choosing the architecture whose inherent compromises match the reality of your system.